to tell us about fixed area states in ADS3 and 0.
Thank you. So I'm going to talk about this paper, upcoming work with Manish, the graduate student in the Institute of Mathematical Sciences, which is, it's my neighbor. It's in Chennai. Okay, so the basic point is that there are things called fixed area states. Okay, and they have these traits called tensor networks, which have been very useful for us in understanding integrated structures all over. Okay, but we don't know much about fixed area states on the boundary. Okay, so today what I want to do is I want to propose a holographic map in ADS3. What is a holographic map? A holographic map is a map from some bulk input space to the boundary input space, which is the UV condition. Should be the UV condition of the bulk input space. Okay. And in particular, one of the things individuals will tell us what the boundary towards the fixed area states are. Okay. And as an input, I'll take a bunch of results about OPE states into DCFT, which have been worked on by a lot of people, including a few in the room. Okay. And on the way, I mentioned that we run into some interesting physics about what the boundary dual of a bulk gauge transformation is, and a new handle on multipartite entanglement and so on. Okay. I'm presenting this more kind of backwards. I started from here, and then here things kept getting more general till I ended up at this. But I will start with the more general thing. Okay. So yeah. Now the basic idea, okay, which is like really the workhorse and a lot of work here nowadays, is that the bulk of ADS-CFT is somehow a coarse-grained version of the boundary. Okay, this is generally true that any time something is emergent, it comes from some sort of coarse-grained. Okay. Now in the literature there are two approaches to coarse-graining. One is taking the boundary to an ensemble over theories. Okay. And in 2D and 3D, we kind of know or expect that there is an ensemble that reproduces pure gravity in the bulk. So in 2D, such single sample proton the ensemble exactly. In 3D, there has been a lot of recent work. Okay. Yeah. But there's another thing to do, which you can coarse-grain over certain windows of states. Okay, and I will be a little more precise about this as we go on. But what this does is it doesn't give you pure gravity. It gives you a semi-classical GR, so gravity is some quantum stuff on top of it, for a code subset of semi-classical states. Everyone's heard of code subspace, but whenever we talk about semi-classicality, it is not a linear condition, so you actually get a code subset. Okay? Mathematically speaking, you want to work here because it's very nice that there are like proof theorems, all that stuff. But it's kind of very good for calculating path intervals. What I want to do is I want to work at the level of states. And I don't actually understand ensembles at the level of states. I know how to think about ensembles when I want to calculate path intervals. So I will actually work in this approach. And what I will find about the sort of I bunch a bunch of things, but what I try to do is that I make a bunch of assumptions and show that the assumptions break down the bulk and the boundary at the same place. Okay. Okay. So let me leave that. So in working on this, I actually had to revisit my own understanding of fixed area states in quite a bit of detail. So like roughly a significant chunk of the talk is going to be me describing three different fixed area bases, projectors, and states. Okay, in pure PR and in semi-classical. Then I'll give a code subset into DCFT and steady gravity, for which the results will actually hold true. Okay, and then I'll propose the holographic map, give you some evidence, and finally talk about the physics of this. Okay, so let me start with fixed area states, and I'll work in pure PR. So the nicest way to think about fixed area. So first I talk about fixed area basis elements. Okay. So in semi-classical theory, the usual way we define a state is by a boundary condition for a Euclidean path. Okay. So as I have drawn it abstractly as a semicircle. One example that you are all familiar with is the thermophile double, where where the length of the semicircle tells you what the temperature of the of the bulk. Okay, and all my bulk states are meant to be states in parentheses. Okay. Now, you can define something called a Wheeler-Dewitt wave function, where you basically take this boundary condition, okay, and then attach it to this boundary condition is an asymptotic boundary. You attach it to what is it? Yeah, you attach it to a slice at finite distance, okay, and put some boundary conditions on that slice, okay, and now you have a closed set of boundary conditions, and so you can use the boundary condition to look for on-shell solutions, okay, and you get some on-shell geometry, calculate on-shell action, and make some choice that there is no interesting topology between this slice and that slice, okay, and that defines the function psi of A. Here A is the here what I do is I put the boundary condition where the extrinsic curvature of the slice is 0 almost everywhere, except that so we are in 3D bulk, so extrinsic this is a two-dimensional surface. These are one-dimensional. These are curves. On these curves, I'll fix their lengths. Okay, and I denote A by A the set of all lengths I fixed, and I define this the on-shell action of this geometry to be psi of A. Okay, and I define the fixed inner basis element by saying that psi of A is inner product of the state psi with some basis element A. This is similar to how we define the x ket in quantum mechanics. Okay, we say psi of x is gram x ket psi. Okay, yeah, and so this is a fixed area basis element. It is not a state. It is not a normalizable state. Okay, same that x ket is not a normalizable state. Okay, one important thing is that it is not a complete basis. I really in 3D GR there are areas in the bulk, and also there are what are called boundary gravitons, which are degrees of freedom localized literally at the asymptotic boundary, and it has been known since Brown and know that boundary gravitons in the bulk map to descendant states in the CFT. Okay, so the actual basis is a bunch of areas and the state of the boundary gravitons. I will mostly ignore the boundary gravitons because they work out quite simply. I actually managed to skip a slide by mistake. Go back. Okay, I'm working in serial share. Okay, this is the usual action. So you have a asymptotic boundary B, a slice sigma, okay, and a bunch of what are called corners or pleats on sigma. Okay, and the action is the usual negative cross-function constant action for the bulk. You get extrinsic curvature given something terms on the boundaries. The asymptotic boundary is further counted out. And on these pleats, there's an extra action, piece of action. What that action does is it basically it's a product of the length of the surface you have whose length you're fixing and the internal angle. Okay, so theta is the internal angle, and there's a sense in which some of these surfaces that you will fix, their internal angles will want to be 0 or pi. Okay, you don't really. In some sense, by want to be, I mean, if something wants to be 0, it is the space is smooth when it's 0. If something wants to be pi, the space is smooth when it's pi. Okay, so in this case, if both of these internal angles are pi, then you can see that there's no corner. It's a smooth slice. Okay, but there will be other cases where things are smooth when it's 0, and whatever it wants to be, you have to subtract that off. Yeah.
Two questions. Are the LIs measuring like some length in the phi direction?
Yes, it's in the direction that I've not shown. I'll show you some examples now.
And then are they just for the purpose of the action? I think things like Lagrange multipliers.
The Lagrange multiplier will roughly be the angle, the internal angle. So theta is really a Lagrange multiplier, and this is Li. Yeah. So let me give you some examples. So here are some examples. So the Euclidean path integral would be like a cylinder, and that we know, and then the bulk slice would be again a cylinder, but with one length fixed. Okay, you get to fix only one length in each homotopy class because in 3D hyperbolic geometry there's a theorem that every homotopy class has at most one geodesic, and for all the cases we consider it's actually equal to one geodesic. Okay. You can also consider a Euclidean particle that creates some entangled state of 4 CFTs. So here you are working at 2 CFTs, here you have 4 CFTs. Okay. And then the pulse slide that you might want to consider would have the same topology, but in each homotopy class you fix the length. Okay. And all of these things, and then you can also go to PCFT. So it would be, you can consider a case of 4 intervals, but the interval in what case is defined by boundary conditions which are drawn as red, what are called Carty boundaries. Those Carty boundaries are dual to end of the world planes in the pulse, which are these red rays here. And again, now you fix not circles but intervals. Okay. So I will focus only on this case mostly in the talk, but it generalizes into all of them. So I'll denote the fixed area basis like this. So here I'll denote this fixed area basis element as just one. Okay, I'm drawing it as a network of fixed elements. So then I'm kind of thinking of drawing a dual graph. Okay, so L1, L2, L3, L4 are the 4 outside ones, LS is the inside one. Okay. So these are the examples. So the inner product between the now you have to I told you what a basis, I will tell you about the inner product. Ket x doesn't mean anything, but we know x ket x per y is delta x minus y. Now the point is that the bulk of GR has a gauge symmetry. Okay, diffeomorphisms are gauge symmetry of GR. And here we fixed a particular slice. Okay, and there are gauge transformations that move slices up and down. So in a ficta slice, I'm talking about a gauge fixed basis. Okay. So normally if I tell you I have ket x, and you'll just say, okay, the inner product must be delta x minus 1. This is called the kinematical inner product in GR. Okay. The physical inner product is a bit funnier. So I denote the physical inner product by x theta. Okay. So suppose you have some ket with some li's and a pra with some li primes. Okay. The physical inner product is given by the partial action of a piece of spacetime to boundaries under 2 slices that we fixed. Okay. So I have to consider this as boundary conditions and calculate the partial action with these boundary conditions. Okay. These 2 points here are the boundaries of those, are the asymptotic boundaries of the Cauchy slice. Okay. And all the black lines are k, I, j, 0 intrinsic curvature slices. Then there's a fact which is easy to prove, which is that if you have 2 k, I, j equal to 0 surfaces, okay, they can only branch from each other at extremal surfaces. They can't branch at a non-extremal surface. So if this is k, I, j equal to 0, this is k, I, j equal to 0, they are meeting here. So they cannot be distinct surfaces meeting here because the asymptotic boundary is not an extremal surface. So what happens is that it gets zipped. These two things have to agree up to this outermost surface on both sides. Okay. So in fact, let us simplification where L2 has to be L2 prime, L1 has to be L1 prime, and then the inner product is just given by the partial action with this boundary condition, which is a fixed area boundary condition. So you get it, and you get these delta functions. You get delta functions only for the extremal surface is very, very close to the boundary. Anything interior, you do not get a delta function. We'll see examples soon. Okay.
Sorry. And so this inner product is now not a kinematic inner product.
Yes, it's a physical one.
Okay.
Also, the comment like your k equals 0, is that like a choice of basis or is it a gauge choice?
It's my basis is a gauge fixed basis. So like
Okay.
so the gauge, yeah, I'm defining the basis as this gauge.
Also, like it is eta equivalent to say like max field and L. They have this group average.
Yeah, this is the group averaging inner product. That's all. But the group averaging inner product doesn't technically make sense for GR. It is yeah. So these people call it just call it a degree map or something. It really works only asymptotically as an asymptotic expression in GR. Okay. Cool. So now let me show you an example. So consider again the four boundary wormhole case. Okay. So the inner product is given by the following. So you have four external surfaces, okay, and four external 1D surfaces, which are the L1 and L2, okay, and two 1D surfaces coming out of them. One of them comes out here, whose length is LS, and one of the 1D surfaces goes inside, and its length is LS prime. So these are the LS and LS prime, and you have to fill up the region between these two 1D surfaces. Example. Okay. So there are many ways. There are, I think, infinite ways of. I believe infinite number of ways of filling them in. So the two ones I will focus on. So first one is just you can identify these two surfaces. Okay. When you identify these two surfaces, you get a delta of LS minus and you get the fifth delta function. Okay. And there is the function action is zero. I have chosen all the all of those factors of pi at these different surfaces, so that the function action of that is zero. Okay. But you can do something funky. Suppose these two areas are equal and these two areas are equal. Okay. These two are equal, these two are equal. Then just consider the ket side, the one of the 2D surfaces. I can identify this surface with that surface, with that surface with that surface. Okay, so I get this object. Okay, I just give this is the ket side. This is a L1 equal to L3 and L2 equal to L4. The other way, and this outside is LS. And similarly, for the inside side, you get another one. Okay, and then these interior circles identified with each other. So you get kind of like a wow. The inner product is given by like a 1D circle which has branching in it. Okay. Anyway, so here all the angles of what they wanted to be, here they're maximally far from what they want to be. So you get the inner product has two, all the exterior L's have to be the same. The first term is one where the last L is also the same. But then there's extra term with extra delta functions and some non-zero prefactor. Okay, and as you can see, like somehow this thing is preferred when LS and LS prime are very big. Okay, and I will show you where you might be like, how did I come up with this? I will show you how I came up with it, and then it will make sense that this is exactly when it should talk. Okay, and then the infinite number of meetings. So the gravitational inner product between fixed area states, fixed area basis elements is quite intricate.
Sorry, maybe it's just me that not understanding gravitation, but so now you at first you call this a four-boundary wormhole. So you're thinking of those like four circles in the
Yes. They will all connect to trumpets in some sense.
Okay, I see.
Yeah,
And
because
those are the
the trumpets are these ones, which are identified. Yeah. Sorry, go ahead.
like in my mind, if you go to the slide before, the way I was imagining this is that the two corners without blue dots, that's the two asymptotic boundaries,
Yes.
right? And then, but then now you're saying I can connect some trumpet to the L's.
Yeah, so what happens is that this part and that part have to be identified because of the geometric theorem about geometric slices. So this L1 and L1 prime have to be the same
Right.
surface. L2 and L2 prime have to be the same surface. So because this part is just identified, the Austrian action is zero, and I just remove it.
Okay.
And I end up with the Austrian action only with some fixed area modifications.
I see. Okay.
Yeah, no, there are no eccentric modifications.
I see.
Sorry,
So
we
that's
should-
what you're thinking of them as multi-boundary wormholes, but with geodesic boundary.
Exactly.
Okay.
Yeah.
And
But like the definition of the inner product involves the trumpets also. It's just a fact about
Yeah.
on-shell geometries, and if you want to do off-shell stuff, that might be important. Yeah. Okay. Okay. So now I'm going to go fixed area basis elements. So now we can define fixed area projectors and streams. So fixed area, so you can consider a projector in the fixed area basis, which is given by some function of the area, where if you take a wave function, that wave function is get multiplied by that function. Fine. Okay. And a fixed area projector is when this f is fixed on some particular length L bar with order g. Okay. So And why bit order G Newton? Because when L bar has bit order G Newton, L bar by 4 G Newton has bit order 1. Okay, this is kind of like a microcanonical project. Okay, and for semi-classicality, you typically want bits of physical things to be order 1, not order G Newton. And L by 4 G is the physical object. Okay, and a fixed area state is exactly a state which is given by a fixed area projector. Okay. Yeah. And what was the thing? Yes. So you construct a state by path integral like the 4-boundary one that we mentioned before. Typically, the fluctuations in the lengths are going to be order root G. Again, fluctuation in length is order root G Newton means fluctuation in the entropy is order 1. Okay, which is like order 1 by root G Newton, which is like a sort of canonical object that you this is like a canonical observer. Okay, and the reason I am emphasizing this is that in the semi-classical limit you only care where you can only care about the case where the projector length and the sort of saddle point length differ by very very small amount, order square root d. Okay. There are all those certainties that you can evade in semi-classical limit because of this. So that's a bit this is pure here. So of course the point is that semi-classical gravity doesn't have a non-reducible space. You really have to take this in EFT. The most famous fact about the fact that it's consistent EFT is the fact that the entropy is given by A by 14 into the length out. Each of these terms is independent, but the sum is not. The sum is, there's been a lot of arguments that the sum is actually very different. Okay, so in semi-classical here, what we're about to do is that on the slides, instead of fixing just geometric boundary conditions, one would want to fix some sort of basis for the EFT inputs. Okay, for this I need to understand the bulk EFT there, and that's quite hard. Okay. So, yeah, but I will consider a particular EFT where things are much simpler and I can actually take products. So, let me define that EFT now. So, what I will do is, you remember that I am defining my statements as Euclidean path integrals. I will demand that these Euclidean path integrals have only stress tensor insertions. Okay, so you have your path integral. Yeah. And then you allow some stress tensors here. But if you want to put a primary, some non-trivial primary insertion, you are not allowed to do it. Only allowed sources for stress tensors. Okay. So if you do this, you get a linear subspace, a linear subspace is equal space. But this actually turns out to include a lot of non-semi-classical states also. And also, so I will put further restrictions which are not linear restrictions. So this surface has some moduli. Okay, the conformal metric of this thing has some is a finite, is sort of finite dimensional space, which is called the modular space. And I will restrict the modular so that bulk fields don't converge. Okay, bulk fields, EMP fields do not converge. And I will also demand to be classical. For neither of these is a linear condition. So this is really a port subset. Okay. What these conditions will ensure is that when I actually consider these sorts of things, the bulk matter is always in the Hartree-Logic state for the solution geometry. Okay, it is in a fixed state, no matter what values I put for this. So in some sense, this is the thing that allows me to define things semi-classical. Okay. Yeah. And here it's important that the thing I told you about the fixed area, the length I fixed at the saddle point length being very close to each other is super important to make this work. Okay, if I took a fixed length very far from the saddle point, then the bulk field would have non-trivial contributions, which I can ignore because of this. So here you can actually show very explicitly write down the fixed area protector in the Chern-Simons formulation of 3D gravity. But I will skip it. Okay. The important thing is that fixed area protector looks like a Wilson line of some sort. Okay. And this Wilson line is homotopy. I can like deform, it will be some operator defined on a loop. Okay. And I can move the operator around as long as I don't break the loop. And it's important that I can move it all the way to the block. I will explain that later. So now let me define my holographic map for these things. Any questions till now?
Maybe help me understand why allow stress sensor insertions but not like very light primaries?
Great. Basically, stress tensor insertions like change of moduli are not that different from each other. Okay, so most of the moduli can be done by integrals of stress tensors. If you want to include all the moduli, so the linear combinations of different moduli look like stress tensors. The other way to think about it is that basically I want things to be in a So this gives you a good code surface. All I can say. If I can allow stress tensor, I will get a very vacuum. And not allowing primary means I'm not allowing bulk matter. Okay. Yeah. So now let me tell you the holographic map. First, I will remind you, tell you some basic facts about holographic CFTs. So some generic irrational CFT with large set. Irrational means that the biggest symmetry algebra is Verasoro. Okay. And generic means that different primarily don't have the same rules. Okay, I'll just take it to be distributed by the definition. It's common in the literature to parameterize things, central charge and conformal weights in a funny way. So instead of talking about C, we often talk about P, which is this function of C, the square root of H for the unit, roughly speaking. Okay, and instead of talking about the conformal weight H, we talk about what's called the Liouville momentum. Okay, the Liouville momentum is either an imaginary number with in this range or a positive number. The point is that when it's an imaginary number, you have a light state. You have to go below the black hole threshold. And when it's a positive number, you have a heavy state above the black hole threshold. Okay? And I will basically consider the case where K is positive. And then there is a density of primaries. So if you take an order 1 window of P and P1, okay, and you can ask, okay, in this order 1 window, how many primaries are there? And it looks like roughly 2 pi over P and P plus P. Okay. And marvelously enough, this is exactly the RT formula for the Z black hole. You can basically show that using the Wilson loop that the length of the external surface is equal to this guy. Okay. And if I plug that in, I literally get L over P squared, which is L over 40. Okay. Yeah. Another object that's important is going to get Philippe location. So here I've drawn that surface in a funny way. Like, there are 4 boundaries here. There are 4 boundaries here. A1, A2, A3, A1. Okay. So this creates a state of 4 symmetries. Now, what I'm doing is I'm putting these gray lines. So what are these gray lines? These gray lines fix you to a particular primary. Okay. They are protectors which tell you that you are living in a Hilbert fixed primary for each of these in each of these Hilbert spaces. So I fix the primary on A1, A2, A3, A1, but I also fix the primary on this Hilbert space which sort of surrounds A1 and A2. Okay. So if you study conformal blocks, you see these things, except you would the stuff boundaries would have points. It's essentially the same. Okay. So we write this as some state P1, P2, P3, P4. So this is some auxiliary primary Hilbert space times this thing. Okay, this picture depends on the moduli of it. It depends on where exactly what these circles are. Okay. Now there's 2 parts here. There's one part which is completely fixed with conformal symmetry and the theory dependent. The theory dependent part is 2 OPE quotients. And the conformal symmetry part is we don't take this. So the product has dots. The thing that's purely moduli dependent has no dots. And I will denote the OP coefficient by exactly this picture but diagonals. Okay, this simplifies a lot of expressions if you have the diagonals. Okay, so these are called OPE coefficients. Okay, and this operator here which takes this auxiliary primary invertible into CFT invertible is called the OPE. So now the point is that you can actually calculate the microcanonical average of various OP coefficients. So we consider these OP coefficients. Okay, so C1 to K, C1 to is the average over microcanonical windows, which is order 1 window in P, which is order 0 window in the length. Okay, it is some known function. I'll just call that known function C1 to 3. We don't. What will be important is the assumption that we're deriving this, which I will talk to you. Okay, so now I am ready to define my holographic graph. So the bicycle is given by an area network. So I'm working in the 4 boundaries again, and some state of the boundary reference. And what this will map to is an OPE block state without the OPE block. Okay, so just have a 4 primary. This is a state in the CFT. P1, P2, P6, and some state in 4 descendant Hilbert spaces. Okay, but optic reference translated descendants in a very straightforward way. Okay, what's important are the 3 factors. One key factor is the OP coefficient in this contraction pattern. So C1 to S, C S equal. Okay, take it normalized in some way. And then this is the other important point. Okay. Now L, all the L's are continuous. But in a good CFT, the conformal weights are not continuous. Okay. So I will actually say that if these L's are part of the factor of focal weight, given the conformal, given the invert case of the CFT, given the spectrum of the CFT, then I get a right side. If these L's don't live in the invert case, then the right hand side is 0, which is annihilated by 0. Okay, so that's what this guy did. And then there's some normalizations. Okay, so basically, and like you draw any fixed area network, that is the discipline. Okay, so this is a natural generalization of what these folks wrote down in 2D. Okay, this is the proposal that we have. It's a proposal here. Any questions about the safety?
Are you thinking of the P states as living in 4 different copies of the single CFT?
Yes. Each P is each P. So each CFT invertible is primary tensor descendant. Okay, there is 4 descendant invertibles and 4 primary invertibles. Yeah, sorry, I should have clarified that.
So, yes, I'm also confused about this point, right? Because if you're doing the OPE, the CFT, like the previous example, I thought you're running a single CFT plane with 4 operator insertions.
They are not, this is not operator insertion, this is boundaries.
Those are boundaries in
This is creating a state on 4 CFTs, or 4 circuits.
But they're disconnected, the CFTs.
Yes. It's a maintaining. It's like the
So
force.
how can you take out the limit if they're disconnected?
It is not an OPE limit. This is just a decomposition of the waveform or something. I'm just literally constructing a state given by a path vector with some projectors. I have not told you yet what like about the model I of this. This is true for any variable.
Okay, like,
Uh-huh.
I'm confused because you're using OPE coefficients and it looks like the same as if you're like contracting A1 with A2 and then you get C1 to S, right? But A1 and A2 are like entire CFTs.
Yeah.
So what does 1 to S mean? Because if those are OPE coefficients, 1, 2 are variables of primary operators.
Is that right?
Yes, while instead you are saying you're using that for a whole CFT.
It's because of state operator performance.
Yeah, but that's
Yeah, the primary
in a
is-
single CFT.
Yeah, so there's an invert case here, there's an invert case here, there's an invert case here.
Yes.
Okay, and then the point is that the pair of bands gives you a map from A1 into invert to S into S. Okay, and that map has as a coefficient C1 to S. There's a path integral on that.
Yeah, you're saying I take a primary from one CFT, I take a primary from the other CFT, and well, it's two copies of the same CFT. You're saying I take the tensor product of those silver spaces and the clutch-Jordan coefficients of this inner product of this tensor product are the whole
Yeah.
coefficients.
So it's not really that Gordon pattern is here actually.
Yeah.
So we will also discuss
That's
this
it.
thing. This is some theory dependent stuff. But yeah, essentially that's it. So the CFT co-product is very different from the angular momentum co-product. So this is the theory dependent stuff.
But I would say that for you to talk actually about a theory, you should sum over 1, 2, 3, and 4 over all possible states of
No, I
this
have put a projector, right?
on a specific over.
Right, yeah. So yeah, the full state would be a sum over projectors.
Yes,
So I can like, yeah.
okay, now, okay.
Yeah. Okay, good. So, yeah, good questions about is this here? Is this slide here? Did you have a question?
No, yes.
Okay, yeah, very great. So you can write this as a tensor network. This is the tensor network. It looks like a complete mess. The idea is that the impulse space goes as input, which is the 1, 2, S, 3, 4. Okay. Each one you kind of copy. So this trivalent junction projects onto the spectrum of the CFT, and then you kind of create a copy like this. The green lines are the descendant things. They can kind of get mapped in an isometric fashion. And the C bras are like the OPE functions. Okay. This tensor network looks like no other tensor network, no other holographic tensor network you see. And I think that's an interesting fact.
So somewhere above the S leg, there should be like a projection.
That's the
That's the C's.
yes. In some sense, the OPE questions are like projecting.
Yeah.
Yeah. Anyway, so this is just for fun. This is not really fun to me, so. Now the point is that I told you about the holographic map of these elements. What happens for fixed area states? So the point is that if you consider a boundary condition state, so something like that. Okay, you project onto fixed areas. Okay, fixed area, and essentially the idea is that the fixed area projector kind of looks like exactly the Gabriel was asking about. Except all of these guys, I sum them primarily over a microcanonical. Okay. So I get some surplus weird OPE results when I consider a fixed area. So yeah. So now that is the thing. So now let me give you some evidence for it. So first evidence is actually the thing I kind of explained already, which is that the fixed area projector can be written as a Wilson loop. Okay. So this is a terrible diagram. I really apologize, but my artistic skills are not up to this project. Okay. So below here we have the Euclidean boundary condition, and above we have the coefficients. Okay, they are kind of getting connected at these 4 boundaries. Okay. And the point is each fixed area surface, fixed line surface is homotopy to some cycle in the boundary. Okay. So these yellow lines are homotopy. Like I can deform this all the way here. Not in this diagram, but when you actually draw the saddle correctly, you can deform it. Okay, the correct saddle, the P, in some sense, the P is inside the C. Obviously, I can't draw it. Okay. So they all this thing. And turns out that when you take this with silver and deform it to the boundary, it's a known operator called Rollinger loop, which is known to fixed project onto a fixed time. Okay, Rollinger defined it a long time ago. But there are really cool and really fun subtlety. So when I deform this operator here, okay, I get a self-adjoint operator on the Hilbert space. So the Hilbert space is on these 4 circles. Okay. So when I have self-adjoint operators, I can identify eigenstates of the same eigenvalue. Because different eigenstates, states with eigenstates with different eigenvalues are common. But this one, the one interior, which we not did at the function, map gets homotomically deformed to here, okay, which is not where the CFT Hilbert is. Somewhere in the Euclidean partial. Okay. So you would want to do some deformation. You would want to do some deformation and to move it to these 2 points. It's known as a CFT co-product, and you can this does a check that you actually do not get a self-return operator on the CFT interface. Which is why different eigenstates of S are not atomic. Okay? And you can see this from our holographic map also. When you take two fixed area basis elements, the inner product in the after map looks like this. It contains this, L1, L2, L3, L4 become the same as L1 for the corresponding primes. But LS and LS there is no inner product, there is no delta function. You just get some combination of OPE functions. Okay? And this is related. So this is again another verification of the fact that this W, whatever is self-adjoint that gets mapped, that gets identified, but whatever is not self-adjoint, there you don't get a problem. Okay? And it's a non-isometric map. So once again, emphasize that this map is non-isometric. In particular, take some bulk states and gives you 0. Right? So it's like it's definitely not preserving enough for that. And for fixed area basis elements, it's not a semi-classical state, so we don't care if this inner product has anything to do with the bulking of the structure. What we do care about is fixed area states, which are genuine states. We have to reproduce their inner products. Okay? And so when you take fixed area states, the inner product, instead of just getting the OPE quotient like this, you get the same thing where every leg is microcanonically arranged. Some over some microcanonical window for every. Okay. And while I was working on this, Tom Hartman wrote down a very general conjecture, which in particular means that this microcanonical average is equal to the Onshel action of the thing I showed you earlier. Okay. That's exactly the Onshel action that we get from the bulk. Of course, some factors which just. Okay. So for fixed area states, assuming this conjecture holds, and we will talk about the conjecture soon. For fixed area states, the inner product is 0. But for non-semi-classical states, for example, the fixed area basis elements, the inner product is not 0. Okay? So somehow the preservation of inner product is related to semi-classical. And I do one example here, but like no matter what network, no matter what fixed area basis element you take, the analog of that statement is conjectural now. Okay?
Do you have a sense of like what types of states are in the kernel of the map?
Things that are too sharply deep, that have too much. So basically, the average spacing in the CFT is e to the minus s, e to the minus a. Stuff that has a lot of features in smaller intervals, typically is the kernel. So fixed area element is a delta function, for example.
In general, will it be like if I try to write a state in terms of fixed area states, like the ones that actually don't see non-isometricity, will I have to like write those superposition in terms of something that scales in order to get something that's going to be in the kernel of the map?
Yeah, you have to look at very crazy like superposition over e to the s. E to the s like good state theory.
Yeah.
This is simply you want in integral theory. Okay, so now let me tell you how this thing comes about. Okay, so how do you calculate the microcanonical average? The algorithm as established by these folks is the following. You find some 2D manifold, okay, in this case it will be genus 3 manifold, such that when you decompose it in terms of confound blocks in this channel, it is dominated by the weights that you wrote. There is some P1, P2, P3, P4, okay? And also in some other channel, it is dominated by the identity prime. So the dots means identity primes. Okay? We need a manifold satisfying both of these conditions. Now the point is that this conformal block, which has no interking OPE quotients, is related to this conformal block by some by what's called crossing equal. Okay, and these crossing kernels are null. Okay, so then you write this as that, and then you just compare these two equations, and you realize that the microcanonical average is a crossing kernel to some density kernels. Okay, so this is the algorithm. So you have to actually find that term. As you can imagine, finding this 2D, this Riemann surface, genus 3, this genus 3 is very hard. So what we typically do instead of actually looking for it, is we consider potential identity channels. Okay, there's one potential identity channel like this, but there could be others. Okay, and see which one gives the biggest macroeconomic average. Okay, and then promote the existence of anchor assumption. Okay, and this assumption is not good thing. There are examples of moduli of genus 3, genus 2, and genus 3 surfaces where it is just not dominant the identity in any time. Okay, so this can happen. Good. So now let me just tell you a minute for the crossing transformations. So you have the usual S2T crossing transformation where you take a primary propagating that way and then consider taking a non-primary propagating that way. There's something called the S transformation, which if you have a non-trivial handle, there are two ways to cut it, like this or like this, and you can consider primary in this invertebrate or primary fixed primary in this invertebrate. Okay. And there's something called the braiding, which is exactly what it looks like. Because I'm considering only scalars, the braiding is slightly trivial, but it's useful to know. And all of these F and S and D, all these things are completely known. Okay. Good. Now in the four boundary case, what is it? We saw that for the four boundary wormhole, there are two contributions there, right? Among each other. Two edges. So, an important, very important fact. So typically what happens is that if there's a heavy operator spin, there is a light operator, which we all often assume to be identity that. Okay, there is a heavy operator in that way, light operator in that. Okay, so any time you dualize a channel, this is called dualization of a channel, you go from heavy to light. So your identity channel should be one where all of the heavy operator channels, so all of these 6 lines are heavy operators, all of them need to be dualized to get to a potential identity channel. Okay? So now there are two things you can do. You can consider these two crosses, okay, and do an F transformation on that. So you get identity and S and S prime. Okay? And because S and S prime are meeting the identity, S has to be equal to S prime. Here delta S is S prime. But you can instead dualize these two lines. Okay? Make S into identity, S prime into identity. Now 2 and 3 are meeting identity, 1 and 4 are meeting identity. Okay? And therefore 1 has to be the same as 4, 2 has to be the same as 3. Okay? And these are exactly the patterns of delta function that we saw from the above. Okay? What is it? This is the usual four-boundary wormhole. I'll just tell you that this thing dominates. You can imagine that there are two boundary wormholes, so 1 and 3 area, 2 and 4 area. The corresponding fixed areas are the same. Okay? And in the Euclidean parts, there's some tube going between these two boundary wormholes. And that is exactly that is the context in which this contraction dominates, and that is also, and I actually, that funny contraction of the inner part of the bulk, I got from cutting of this surface in multiple ways. Okay? Yeah. Good. So you can see that, that there is an exact matching. And you might ask, okay, there's a delta of 2 minus 3. What happens if 2 minus 3 is 2 and 3 are very close by, but not the same? So what can happen is that some bulk field might condense. You might nucleate an entangled pair like this. Okay? So that's exactly when as we go close to the phase transition between that and that, is exactly when the EFT phase. Okay? So you can see that there's a matching from there also. Okay? And when the bulk field condenses, that also means that there's no activity further. So these are dual statements. So let me just quickly tell you some physics purposes. I have 5 minutes left, yes. You can do the following. you can consider the inner product, there should be, sorry, the inner product between a fixed S state and fixed T state. Okay. That corresponds to the Gaussian action of these boundary conditions. Outer boundary condition is same as one below, before, and the inner boundary condition you fix the length in this cross channel. Okay, and this is actually two tetrahedrons are glued to each other in a funny way. Okay, I refuse to figure out, but this is no. Okay, and the Gaussian action is known to be this object. It's called the Virasoro 6J symbol. Funny enough, there's a book about 6J symbols here. Okay. The cool thing is that this region in the middle that fills it up can be Euclidean or Lorentzian, but it has to be one of them. Okay. So there are cases when like this LS and LT are like the past and future. Okay. Yeah, this appearance of 6J symbols actually kind of was anticipated in a toy model that I wrote on Chris and Annie a couple of years ago. I think we'll talk about it on the Berkeley tutorial. Okay. Now I find this very fascinating. So first thing to notice is that this basis change is done by the codimension 0 region of space. Okay, which is kind of like and the reason there's a codimension 0 region is that there's Hamiltonian gauge space. Moving this Cauchy space to that Cauchy space, as long as the boundaries are the same, is a gauge transformation of gravity. Okay. So actually it was suggested in Parikar and Saki identify that Hamiltonian gauge transformations are basis changes. Okay, they're not physical changes, they're gauge transformations, but they're basis changes. Okay. But we realize that picture in an importantly approximate sense. Because when you look at a complete autonomous basis of the UPE process, the S and T labels are not there. Okay. But we are literally doing a basis transformation between labels between base elements that don't exist. They are only approximately base elements. Okay. The second important thing is this unitary matrix elements. Matrix element depends on all of these labels. Okay. What that means is that this basis transformation, if you think of some approximate Parisian such as HL1 tensor, HL2 tensor, tensor approximate Parisian factorization between these 5 lengths because they are independent objects which you can use separately. And there's a factored bulk factorization between these 5 lengths. Okay, and these are different tensor factorizations. If they are same tensor factorization, then this guy will not be able to depend on 1 to 3. Okay, it's not a basis element just in the S level, it is a basis transformation the full in the full 5 lengths. It's a new tensor factorization. Okay. So and the tensor network representation of B has this input which depend on the tensor factorization of the vertices. And so the Hamiltonian gauge transformation is literally a transmutation of the tensor network, not just some simple unitary action of the tensor network. You have to change the tensor network completely. Okay, there's something that I'm implicit in some work, some papers I wrote. One paper I wrote in Hamiltonian, and also there are discussions with Anirban, who's a grad student at CMI, Tanma the postdoc, and Shashank, who's a project student. He's applying for PhDs. If anyone online is watching this, please type Shashank. Okay. Yeah. Okay. The other good thing is that this fact that the SNP surfaces can be causally related to each other harkens back to the original derivation of the non-limiting elements. So these folks proved that area don't come into the following. Considered this area, which is like a kind of like an S channel, okay, and consider the Hamiltonian flow on phase space of this area. What it does is it takes this surface and keeps it like this. So after the Hamiltonian flow, you get before the Hamiltonian flow, the T RT surface looked like this, big one. Afterwards, because of the steam, it kind of becomes this other guy. Okay, because the length of the T RT surface becomes bigger. Okay, and exactly if you consider like you should also draw fix the areas of 1, 2, 3, 4 artificial surfaces. The region in between will be exactly the sort of tetrahedral that I showed you. Okay, the Lorentzian case. So it directly connects with that. In fact, you can say more. In fact, that basis chain matrix element, an appropriate integral of that reduces the commutator between two area objects, two crossing area objects. So it's a fine-grained version of the area commutator, which is known to be some sort of multi-parted integrable measure. And you can also use this in some sort of basis changes to find fine-grained versions of reflected property. And you can keep doing these sorts of games. Okay, so let me conclude. To summarize, that was quite heavy talking method, but what the main central theme was I proposed a holographic map of 3D gravity in a particular code subset. Okay, where no bulk is except. And the map did was it took a fixed area pixel element. Okay. Check first thing it is check whether any of these all these lengths are in the spectrum of the suit. If it's not, it is 0. If it is, proceed. Okay. Each length becomes a primary. Each exterior length becomes a primary. Interior length is not. And this same network becomes a network of dimensions. And then there are some non-dimensions. So this is the holographic map. And the inner product could be bulk and boundary match exactly wherever the conjecture of Hamiltonian is true, or happy to remove it safely. Essentially, the breakdown of applicability is exactly what to say, it matches on the bulk and boundary. Okay. So there are many questions. I have endeavored to formulate these into one loop corrections of element. Okay, so one should be able to calculate one loop corrections. One question is that I told you we are finding multi-parted entanglement. We find multi-parted entanglement measures. What can we learn about it? What can we learn from these measures? I don't know. I told you about states. Now I'll tell you about operation. What is the dictator projector? It's actually quite a heavy question. And some technology that these folks developed into DRDO is probably useful. The two things I really care about are to understand the tensor network transportation as a manifestation of bulk asymmetry and to do time dimension. These are for me the four areas. Okay, thanks.
Couple questions. First, at the beginning, you mentioned that you only want to consider the real P's, basically, the ones that are linked.
Yeah.
But because we also know that as long as it's heavy, if it's below the threshold, it also exhibits some of this averaging.
Yeah, in fact, you can generalize the story to that.
Yeah.
With enough percent results. I think that's possible. I didn't follow it.
Great. That was the first question. The second question is, I know here you only wanted to consider like sort of simple topologies, right? In which like, the thing connecting the two L's was just sort of like a two. But I guess the thing that I'm a little confused about is you reference this paper by Google operators. In that situation, they saw this discreteness because they were considering the more complicated topologies.
Yeah, so let me just go back. So I'll just tell you exactly where I put in the solution. That's an important perspective that I really appreciate anyone has. So when I defined the real wave function, I said there's no topology in this part. Okay? But when I did the inner product, I never said there's no topology in this part.
Okay.
That's exactly what Google did.
I see. Okay, great.
I literally copied that part from this.
I have that.
Yeah. In fact, you saw that there was some crazy topology that
Yes.
Yeah. In
in my tensor network model with Tom, we were only able to discretize this time symmetric slice of some black holes. But I guess you were mentioning at the end, like you were thinking about time evolution of tensor network. So can you also discretize like
Yeah,
this size?
so essentially, actually, the paper I wrote in Aaron does that. Okay, just in a different language.
I see.
And I need to sit down and translate it to your language. So
Nice.
it's like there's basically essentially the so what I'll just tell you in some detail because it's fun. So what you did was you considered like a bunch of operators like this, matter things, and you considered your bond dimension to be given as S of E. Okay, very put that very broadly. But as I told you, it's not really E-area, but E-area primarily. Okay?
Right.
When you go up, it's going to become visible. Okay? So now you need to have some, so this tensor network transformation story we first noted in this case. So you have two crossing shells. Okay, we consider a Wilson loop here, a Wilson loop here, a Wilson loop here. Okay? And the values of those Wilson loops is obviously the bond basis for. So you can consider the tensor network for this length. But you can consider a Wilson loop here, and that gives you the bond dimension for that side also.
Oh,
So this is yeah, it's like implicit in the paper with Aaron actually. It's like I had already written an entire paper before I found your paper, and I was too lazy to do it. Okay.
Do you know if there's been any like new work on this like CTV like?
I think it's asking that.
Yeah,
what?
I was gonna ask if there was any new work on like the CTV conjecture from Tom.
That is the connection that you found.
Yeah.
I know, but I since the fall, they've been like trying to verify.
I mean, that conjecture is not very different from what we reserved in pure history. So,
Okay, so I guess all of those things are.
Yeah.
Okay, so there's been one thing, like I think there's, like people have checked it at one loop, like you probably pointed out to some paper, like where they computed this, like the partition function of this tetrahedron towards a one loop order, some math.
No, the paper I have paper does not. I talk about it one.
Okay.
But it will be some other does.
Yeah, I think there's a paper.
Matches.
Huh?
Matches.
What? With reserving to that?
Yeah. Yeah.
Okay, any more questions? If not, let's start.
For speaker dinner, during